we have concerned ourselves with solution, numerical solution to initial problems, initial value problems for differential equations, ordinary differential equations. As the name suggests, they start from an initial value, so this is your start of your interval, and you would like to solve this differential equation on a certain interval. Okay? So that is your interval in x. Solving things numerically means if I'm solving for a function y numerically, I'm looking for values of that function on a discrete set of points. Okay? That is a numerical solution. You cannot get like a continuous function. If it appears continuous, that's because it was sampled really on a really fine grid. But other than that, it is a finite set of points that I have that I'm looking for a value of the function at those set of points. So first you discretize, and here there is quite a large discretization shown. And then in all these methods, what we're really doing, you start from a value, okay, that you have at the current time. So initially you just have this initial value that is your boundary condition for the differential equation. From there on, you kind of step for this step size h that you have in the problem, which is how you're discretizing your domain. You basically just decide on a slope you're going to take. Okay? And in Euler's method, which is the first method we tried, it's a very simple slope. You just really take the derivative of the function at that point, which is given by the problem itself, because the problem actually that you're solving is dy dx is f of xy. So derivative dy dx is given by whatever it is that you have on the right-hand side, and you can evaluate that. So that's the simplest method of them all, which is called Euler. All other methods really improve that slope and try to get it more accurate. So the first improvement that we've done is so-called Runge's method, which basically says, okay, take the slope that you had with your Euler's method, then take that route and get to this next point and see what is the slope there. And you take that slope and this first slope and average the two, okay? And basically take that average as your final slope. That's all, okay? And that indeed we have seen in the code last time, that indeed improves. You get something like this in this problem. So there's like a true solution, and there's this Runge's method that really gets closer to it, even for this relatively coarse discretization, okay? And of course, as this, all of these methods, the way their errors work, they depend on h. Okay, step h, so that as step h gets smaller, they get better. Okay. So today, we're going to improve that further. So all of these methods, they could technically not just average two slopes, they could go over, figure out what n types of slopes are on this interval, and then take a weighted average of those n slopes. And that sounds scary, but there is actually reason to that. The way people devise these methods, we're not going to do that, but that would be, for instance, your second course in numerical analysis, is you would actually do the Taylor series on that function. And you would basically develop these Taylor series, and you know how Taylor series has h and h squared and h cubed and h to the 4 and so forth. And you were trying to tailor these slopes to actually cancel some of these and simply remove that error. And that can actually be done. Okay? So as you cancel more and more terms, you actually get a method that is more and more accurate. And that's why we're not going to concern ourselves with devising these methods. But basically, it comes down to looking at Taylor series and analyzing it, and devising a method that will cancel a lot of these terms, a lot of the terms in Taylor series. So here's one that does the following. It's called Runge-Kutta, or I say Runge-Kutta or Runge-Kutta, depending on whether I'm emulating English or German. So you will hear both from me. So this is a fourth order method. Fourth order basically refers to canceling up to 4 order terms in Taylor series and getting really accurate. Okay? So if your method is sort of on the order of h to the 5, meaning that when you reduce h 10 times, you will get 10 to the 5 times more accurate. That is an awesome method. Okay? So that is something that is really good. So what does this one do? It starts with the first slope, k1. Okay? This is my slope from that Euler's method. Okay? And I'm calling that slope k1. The next slope, I take basically that slope for half an h. Okay? So I go to the slope at xi plus 1/2 h and yi plus 1/2 k1h. That means that I took this slope for half of the interval. Okay? And I look at what is my f at that point, which is basically slope at that point, because I'm looking at my f is my derivative, right? So that's my second slope. Then I have this second slope. I take this second slope also for half h and see what would, at this new point, what would be the slope, k3. And then final one is just my slope that I take this k3 for the entire interval h. This looks a little esoteric. And at the end, I have 4 slopes, so I take a weighted average. 1/6 k1 plus 2/6 k2 plus 2/6 k3 plus 1/6 k4. So these weights, which are 1/6, 2/6, 2/6, and 1/6, when I sum them up, I get a 1. Okay, that means a weighted average with different proportions and different weights given to each other slopes. And again, understand that there is actually a reason, and one could analyze the Taylor series and get why do these specific choices for slopes and weights actually work. Okay? So here's geometrically what I'm doing. Okay? Again, I'm starting from xi, yi, and I'm estimating first slope, k1, which is this red thing, at that point. I'm taking that slope where it takes me for half an interval, right here. Here is where this is my function that I don't know, but I pretend that I know. What I do know about it is what is dy dx, or slope of that function at any point, because that's what's given with function f. My problem reads dy dx equals to f. So I evaluate f to get my slope k2. Okay? Then I take this slope k2 right here. That's the slope k2. I take it also for 1/2 h. And I check out what would the slope be to this function at that point. That's this slope. That's my slope k3. And then I take my k3 slope for the entire interval h and find out what would slope be at that point. That's this red right here. That's my slope k4. Those are my 4 slopes. And when I take weighted average of these, 1/6 k1 plus 2/6 k2 plus 2/6 k3 plus 1/6 k4, I get right here. And my exact solution is pretty damn close. Now, this is just a sketch, but indeed it works. So we're actually just go ahead. So there's a whole variety of all of these methods where you could have averaging of 1 slopes, 2 slopes, 3 slopes. We're going to just really focus on this 4th order method. So let's actually implement it and see how accurate it gets close compared to our 2 methods that we tried before. So I'm going to go and start up. I think I have start up. Start up Jupyter. And I'm going to walk myself over to that Lecture 8. I did post, if you want to start from the same Jupyter notebook, I posted it on Canvas so you can download it. Where are my lectures? Lectures. Okay, so this was my implementation of Euler's method, and then there's this Hoynes method. And I'm just gonna cut, copy, paste one of the previous ones as a template. And then improve on it. So here you actually have all of the slopes you're supposed to come up with. So this initial slope from Euler's method is actually here called K1. And then my K2 is f of so here I have a shift of 0.5 h and yi plus 0.5 h. Note that I'm estimating I in terms of I minus 1. If it's easier for you to work with I plus 1 and y of I, you can actually go use the for loop below. If it's the same thing. Oh, and this is times K1. And then K3 is something similar, just using K2. And finally K4. H. Oh, okay. I have coded up such a powerful method that the light started flickering. The electrical system here could not deal with the fourth order accuracy here. This should work. Let's assume that I didn't type. So the average should be fine. 12216. I should leave more empty spaces so it's easier to debug. Spaces help with readability. F of xi. Next one, 0.5h, 0.5h, h. When you align things, you can verify better if they're correct. Okay. As far as my eyes can see, which is not far, and of course the moment of truth will be when I plot the results. I'm going to call them x4, y4 and plot them right against my Euler. Are we ready for the moment of truth? I'm going to probably have to execute all of the ones before just to get the... Okay. Look at that. I can't even see the difference between analytical solution and Runge-Kutta. How's that for being on point?
Can you explain again why in the weighted average for the slope is different for K1 and K2? Like why you multiply?
It's just a variation of different slopes. Okay, so I'm figuring out 4 different slopes. Okay, one of them is taken at this initial point that I'm starting from. 2 of them are actually, this second one is, I'm taking this slope K1 right here for half a step. Okay?
Oh, so that's why you multiply by 2.
Yes. So it's like half a step, yes, and half a step. Otherwise, I would take it for the entire step like this 4, right? It's a slope, right? So it's literally your x times slope gives you how far up you're going, right? So if I'm taking it by half a step, it's half a step times slope gives me this, right? That's my delta in y direction. And the same here for K3. Did everybody get this? Are you getting there? Little typos sneaking up on you? Little typos, big typos. And again, these choices seem esoteric, but they're not from thin air. You can actually, there's a method of how you arrive at those. Did everybody get this magical result? Getting there? So most of the, in terms of implementation of these methods, since we're not busy deriving them and figuring out, hey, it's like I could, for your final, I could and I will give you any of these, okay? And say, hey, here is a problem, please implement a method, okay? That has, for instance, 2 slopes that you need to estimate, and this is how you use them up ultimately to improve your problem. Okay? So none of them will be actually worse than Runge-Kutta. So if you can figure this one out, how to type in correctly, you should, and know the logic of how to do that, then you should be set to go. Yes? Everybody got this? Can I move on?
Are you gonna post that?
These are already posted.
Oh,
The slides are already posted. This is in slides. I will post this, yes, I will update what I posted. So I had up until Friday, so I'll just update the same code right after the class, actually. So it's really just this one. So it's really just about typing in all of those K1s, K2s, K3s from this. That's what it comes down to. Okay, so this is fourth order. Now, everybody, after seeing a result like this, would say, come on, if it shows up. Is this the electrical problem? Okay, all right. So when you see something like this, you're like, well, okay, we're done. Let's just all of the time use Runge-Kutta. This comes down to just like everything else in computation, okay? If you need to do 1,000,000 operations, and in those 1,000,000 operations, instead of computing one slope, one execution of f, you actually have to have 4 execution of f, and then extra additions and multiplications that go into this. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9 extra additions, and 1, 2, 3, 4, 5, 6, 7, 8, 9 extra multiplications. Okay, times 1,000,000 adds up. So if that is a problem, if it's 1,000,000, it's actually okay. If it's 1,000,000,000, it might be a problem. So if you're constantly doing this, okay, and need to execute this, then actually going with something cheap and dirty like Euler method, just execute f once, as opposed to adding 3 more executions of function f, okay, and 9 extra additions, 9 extra multiplications per point that you're calculating, and maybe you need to do that again billions of times, then that can add up. So this is where you have to weigh your time involved that you need to solve your problem and how many times you need to execute. Otherwise, this indeed is a much more accurate method if you can afford it. Okay. So that's why a lot of people choose anything in between a first order and fourth order method, depending on a problem. There are some problems whose change is so rapid, like exponential functions, that first order methods just cannot do. You will get such bad results that you basically cannot bear them. And you do have to actually go with a higher order method. So you have to look at the problem you're solving and evaluate how the method is doing. I think this should be basically a message of the entire course. You always have a range of numerical methods that are approximating your solution, and you will have to, based on the problem you're solving, you will have to tailor which one you're going to use. Okay, and then one final small topic that we're going to cover is actually, we know everything about it already. A lot of times we need to actually do systems of equations, simply because results of one function are influencing another. And in mathematical methods, the favorite choice of that is sort of predator and prey. Basically, if I have number of lions, okay, the change in number of lions depends both on the number of lions and number of whatever it is that they eat. In this case, it's a simple system of just gazelles, right? And then the only thing in this system, in the system that has only lions and gazelles, nothing kills lions. Otherwise, we need to include people, okay? But we don't have people. So people or the spread of their seeds. So people might not directly kill lions, but they might reduce their habitat. Okay? So there's that. Okay, so in the system of two, predator and prey, this is relatively simple. And then number of gazelles depends on the birth rates of gazelles and how many, so this is my change in number of gazelles. It's the birth rate times the number of gazelles, but also number of lions that eat gazelles, right? So I have both, death of a gazelle most of the time is related to a lion. They don't often die of natural causes. So essentially, I have coupled equations. The change in the number of both lions and gazelles is no. Now you could translate this, and I will in one of these upcoming times, the oil prices, demand. So basically markets work similarly in terms of price of anything. Depends on supply and demand, and in the simplest case you can couple the two. Okay? So, and especially when we have price of anything that depends on of something, having something else available. So basically you can have all of the gas in the world. If you don't have pipeline to transport it, the price of that transport will limit what the price will be ultimately of gas. That's a simple example. So a lot of times in most applications we have coupled equations. So in that case I'm solving them simultaneously. And I can basically do the same principle. So let's say that I had two coupled ODEs, dy dx is f1, that depends both of x, y, but also on z. And dz dx is some other function f2 that depends on x and z, but also on y, which is my lions and gazelles just from a moment ago. My numerical solution in the simplest case of Euler's method is pretty much the same. I have step h, and here I evaluate this first function, f1, of all three parameters that I have. And same for the second one. Okay? And I update, for every for loop, I update them simultaneously, okay, in the same for loop. And then I move on. And it's this older zi that plays in both places, and older yi that plays in both of them, okay, plays the role. And if I have a more complicated method, well, I do the same. This is how Runge-Kutta, this is how Runge-Kutta would get ugly, okay, if I did it for this same problem, because I have to actually do 4 slopes per my equation that I'm showing, so that's 8 slopes altogether. But nothing in itself is much different from solving one single equation. I just have to carry both equations. Now there's one more technically. I could have coupled n equations and not just 2, so this can just keep going. And all of the methods that we have basically apply. Now, there's also another place where I could actually involve coupled ODEs. How would you transform this problem into 2 equations to be solved simultaneously? Somebody's smiling. Did you have this problem in ODEs?
This looks like I did, yeah.
You just had that on homework. Oh.
We're not very good at translating information from different topics.
Well, let's try. So how about I start from my boundary conditions kind of guiding me, okay? So how about I call this z of 0, and my new function z is actually y prime. Yes? So z is equal y prime, or y prime rather is equal to z. Yes? Now from this first equation, what is y double prime in terms of z? And I have to. Z prime is some function of t, in this case, x, but I call it t, x, doesn't matter. Right? If you want x, I can call it x. It's some function of y, z, and that variable. In this case, very simple function. The function f1 is minus 4y. Okay? So this is what I call f1 of t, comma, y times z. Okay? This is my function f2 of t, comma, y times z. And I'm going to move t to be x so that we have a complete resemblance to what was on the previous slide. From here. This is what I was given. Yes? It's a little bit of manipulation. Yes? So this is now a system that I could solve with Euler's method or any other. Okay. Okay. I will stop here so you have the time to do your course survey. If you are curious how to solve this, that example is actually solved on your slides that I already posted. Okay? And just the final comment is that whatever you learned about Python is just a start. Okay? It's a language that has right now a lot of future and is used in everything and anything, and you have just scratched the surface. Don't let that stop you. You know how to study. Go and find, and there are online courses. You can expand your knowledge in any way possible. If you need help with where to go, do let me know. Whether it's Python or any other language, reality is the following. In your lifetime, if you're dealing with numerical solutions, you're going to learn more than one. Okay? I've learned a number. I started with something called Pascal that none of you know anything about, and I did quite a bit of courses in high school and college with Pascal. Then I switched to C, then to Fortran, then back to C. Then I introduced MATLAB, and here we are in Python. Okay? So, and I often combine multiple of those because different sources that I work with use different. So be open-minded. You can always learn. There is always resources to learn. Don't let anything like that stop you. And you will have to change. Technology changes quickly, and that's one thing that we know really well. So this is a good start. You have to maintain a skill in order to actually be good at it. Okay? So practice makes it perfect. So try to use Python as your kind of extended, or any other really, but as your extended arm in solving your problems in thermodynamics and transport phenomena and so forth. If you need to visualize something quickly, if you need to quickly share with your colleague through notebooks, that's really easy. That's one feature of Python that I really like. Okay? So it's easily integrated with all kinds of other solutions. So this has been a pleasure for me to actually learn Python with you because this was my first time teaching Python. Okay? So I learned it this summer and I brushed it up with in this course with you. So I hope that this was helpful to you as well. I am available for questions via email. And the final is on, I will post the final information. Final is next Monday. I posted the practice questions already. All right, I will get out of here. So you
R-Y-M-E-R.